of that region, it will collapse into a black hole. All right, now, let's assume that the minus first law of physics is correct. Information is never lost. Then the initial information content, the wine, the cheese, the alphabet soup, the information could not have been more than the amount hidden in the black hole. If it was more, that would mean that information was lost. But we know how much information is hidden in the black hole. It's the area of the horizon in Planck units. The conclusion is remarkable. The maximum amount of information that can be held in a region of space, this room, is proportional to the area of the walls of the room. It is as if the walls of the room were divided up into little tiny pixels, one Planck area on the side, and everything in the room could be described by knowing what was going on in those pixels. That's the argument. It's as simple as that. And the conclusion of it is that you can describe a region of space, by data on the surface as if it were a hologram. The maximum amount of information in a region of space is proportional to the area of the region. I like to say that the world is a pixelated world and not a voxelated world. Let's move on. We have a few more minutes yet, I think. Let's talk about cosmology. The reason I want to talk about cosmology is because there is another sense in which the world is a hologram. Closely related sense, a very closely related sense. There are other kinds of horizons in the world besides black hole horizons. Let me explain to you the other kind of horizons that cosmologists, real cosmologists, not half cosmologists, are constantly concerned about, and tell you how they play into the story. Here's the universe. Now, of course, this is a tiny, tiny little piece of the universe. It's the best I could find on the internet when I looked up Starfield, and but you know, we were interested. How big would you say this? It's pretty small. Tiny, tiny little piece of the universe. Tiny, really, really tiny, right? But nevertheless, expand your imagination and let's pretend this was 10 or 20 billion light years on, 20, 25, 50 billion light years on a star. I don't know, some big number. Okay. Let me give you a model for the way the universe works. It's another fishy example, another fishy story. It's the way, it has to do with the way the universe expands. It has to do with the way the universe accelerates as it expands. Let's go back to the lake. Let's take away the drain hole. We're not interested in the black hole anymore. It's there. There are black holes all over the place, but let's just take them away. They're not interesting, but there's something new. The lake is being fed from underneath by a uniform collection of pipes. And these pipes are bringing in, I see Dick laughing, are bringing in new water. What is the effect of this new water? The effect of this new water is to cause a puddle to expand, to grow, to stretch. Portions of it will separate from other portions. And the effect of it on these fish, incidentally, this is Bob. This is Bob. This is Alice. And this is Charlie over here, but Charlie has nothing to do with anything. So, the water is being pumped in. And as the water is being pumped in, the lake spreads. In fact, the way the lake spreads, if you work it out, is it spreads out according to a law that the further apart that you are, the faster you will be separating. This is called Hubble's law, but this is a special case of Hubble's law, which is called the accelerated expanding universe. Now, Bob is sitting there and he's communicating with Alice. But Alice is being dragged along by the flow, and so she's separating away from Bob. Eventually, a point will come where what happens? Where she passes a point of no return. A The point of no return does not have to do now with inflowing fluid. It has to do with outflowing fluid from the point of view of Bob. At some point, the fluid is flowing outward relative to him faster than the speed of sound at some distance. And at that point, when Alice crosses that point, she can no longer communicate with Bob. She has passed through, let's call it an external horizon. It does not have to do with an inflow and a drain hole. It has to do with an outflow and expansion. Well, this is exactly the way the universe that we know works. It is expanding. It's expanding with the same pattern of acceleration as if it were being fed new space, as if space were constantly being replenished, therefore being pushed apart, and it has a horizon. Each person has their own private horizon, namely the region around them, which is moving away from them with slower than the speed of light. That region they can see, what's beyond it they can't see. So it looks something like this. This, of course, is not at all what it looks like. It's about the best I can do without, I didn't want to draw CMB maps. But that's what it looks like. Here's Bob at the center, and at some distance out, there's a point of no return, and if Alice crosses that point of no return, she's, as far as Bob is concerned, out of this world. Simply out of communication, never to communicate again. She's gone. There's a puzzling thing. It looks like there's a region of the world, maybe most of the world, which is out beyond all possible observation. What do we actually know about it? In fact, we know a good deal about it from observation. We know that the universe is at least about 1,000 times larger in volume than the region that we can ever see. Ever seen means within the horizon, within our horizon. The universe is at least 1,000 times bigger in volume than the horizon region. So there's stuff out there. That stuff is completely beyond observational science, period. Well, maybe not. But, at least in a simple sense, in the same sense that you can't see what's behind the horizon of a black hole, that stuff is out beyond the ken of any known method of observation. What is the meaning? I mean, this raises deep, both philosophical questions, scientific questions, puzzling questions that really do bother all people who think about this. What is the meaning of all this stuff out there, the scientific meaning of all this stuff out there, if it can never be detected? How can we ever hope to confirm it by real observation? What is the proper description of a world that is bigger than the cosmic horizon? These are all the same question, of course. But finally, is our cosmic horizon, the one surrounding us, is it a two-dimensional scrambled hologram of all that lies beyond it? These are questions which are deep, profound questions, and the only thing, I am not going to answer them, the only thing I can say now is we are all wrestling with them. And they're big questions, and they're hard questions. That's the physicist itself. Universe. So I hope I've given you some flavor for the kinds of questions which we ask. But I want to convey something to you. That it's an extraordinarily remarkable fact. It's not a fact about me, it's a fact about the way human beings think, the way human beings, their cognitive abilities, that when you think about it for a moment, a small, relatively small band of hairless apes has been able to deduce all of this, has been able to deduce such strange and totally unintuitive, very, very foreign ideas, very, very abstract ideas about the universe as peculiar and as unintuitive as the world is a hologram. Thank you.
can take voxels and turn them into pixels.
You know, I have a funny thing. When I lecture, this is microphone, I hear real loud, and the effect of those make you a little bit deaf by the end of the lecture. So it means you got to really yell loud.
Sure. So if you can take voxels and turn them into pixels, why can't you take pixels and then just turn them into linear memory?
Yeah. In principle, you can, but you can't do it in such a way that there's only one bit of information per Planck length along the line. This has to do with the properties of gravity and has to do with the fact that Newton's gravitational constant is an area and not a length. In principle, of course, you can always take any data in any dimension and map it to the data in a lower dimension. But the cost is usually not just scrambling, but the cost is usually that you've got to make it infinitely dense, denser and denser and denser. But what's happening here is different. What's happening here is we're saying that we contract the dimension of the description. Nevertheless, the number of bits that it takes is never more than one per Planck area. And as far as we know, it is not possible to go past that. There's no evidence that it's possible to go past that. It's a good question, it's a great question. I think to give an answer would require more technical stuff than I'm going to, yeah. We can write some equations on the blackboard, but I don't want to. Send me an email.
I was wondering about something with the fish analogy. And
Which fish analogy? Either of it?
I'm sorry, I beg your pardon?
Which of the two?
Well, let me explain. I've actually maybe got two questions, but based on the first one, the second one may not be meaningful. If I understand correctly, when you fall into a black hole, according to general relativity, the time dilation effect becomes effectively infinite. So from when Alice is falling into the black hole, from Bob's perspective, in a very real sense, she never actually crosses. So if that's correct, I'm wondering why that doesn't alone sort of help that whole initial paradox. It seems like the answer is no, but I can't put my finger on it.
It's a very good question. All right. From Bob's perspective, Bob watching sees Alice slow down, and slow down, and slow down as she approaches the horizon and never quite gets there. It's time dilation. From Alice's point of view, it takes a finite amount of proper time, wristwatch time, for her to cross the horizon. So there's already a tension there. It is true that from Bob's point of view on the outside, she never does cross the horizon. But in classical physics, the picture is she gets closer and closer and closer and closer. Then you can send, and eventually forms a kind of sedimentary structure that just slowly migrates closer and closer, getting thinner and thinner. Then you can throw another Alice in. And there's always room for another Alice, closer and closer to the horizon. And then you can throw another Alice in. And you can keep doing it, and keep doing it as these shells migrate closer and closer to the horizon. According to classical physics, you can eventually get an infinite accumulation of data arbitrarily close to the horizon. So the paradox, when reformulated in the language, which would be the language you're using from the outside, is it looks like the horizon should be a place where an infinite amount of data can sedimentarily, I don't know what the right word is, but accumulate. The fact that it's finite becomes the what is it that obstructs sending in more than a certain number of Alices, given that they just Lorentz contract and get thinner and thinner. So there's other ways of describing it. But you do have to contend with the fact that despite the fact that Bob never sees her cross the horizon, Alice, in her own frame of reference, says that at 12:45 exactly, I crossed the horizon. So the tension is already there, and you're right, it is already there. Oh, there was a second question.
Well, I guess I was wondering.
Incidentally, the same thing happens with the fish. Yeah, it does. Bob watching or listening Bob listening to Alice yell, L, L, L. As she gets closer and closer to the point of no return, her signals come out more and more redshifted, more and more. And so he hears her slow, and he never hears across the horizon. So it's also the same thing is true there.
Right. The other part of my question I was getting at, I guess, is initially I was trying to figure out why that fact isn't of any help in resolving the original paradox.
It is part of the story, but if you want to reframe it that way, then the question becomes, what is the obstruction of having an infinite number of
Okay.
right. It is a good question.
I'm a little not clear. Does Alice experience the billions of degrees of temperature you talked about as she crosses the event horizon?
No. Not unless Bob tries to check her. You know, for many of you, you know the story of Heisenberg and trying to find out whether you can detect both the position and velocity of a particle. And what he says is, if I try to detect the position of a particle by hitting it with a photon and focusing that photon, in order to detect its position to within a certain resolution, I have to hit it with a photon of small enough wavelength that that photon has enough energy to give the particle an enormous whack. And thereby, any attempt to try to show that it has both a position and a well-defined velocity will wind up giving the velocity a tremendous and random whack. It's the same kind of thing here. Any attempt to try to determine whether Alice is being fried at the horizon will fry her. So it's one of these quantum mysteries.
Just following up on that, even if you don't, the physicist doesn't look at Alice,
You know what?
the Bob, it doesn't shine like Alice, but nevertheless, it's seeing something new that sees Alice before she falls into it, or before she crosses the horizon.
How can you see her?
Before she crosses it.
Yeah, how can you see her? How can you see her without detecting light coming from her?
Right, oh, okay, so, but well, it's the source. But if there's like an ambient conditions, she's radiating,
Yeah.
infrared, and so, does that like get blue shifted? Is that what's to Bob? Is that what happens?
No, redshifted.
That gets
It's
redshifted.
redshifted more and more.
How does it-
But Bob wants to get a clear signal. He's got to collect photons from Alice, which from her frame of reference are extremely high frequency. Where does she get those photons from? Either she had a source of enormous energy to radiate out, which would probably destroy her anyway, this is an enormous explosion, or Bob has to shine light on her, and same problem. Yeah.
Well, that's it then. I guess, why don't we thank Lenny for a great
Thank you.